think it's a good time to start. I'm delighted to welcome our guest speaker today. Our guest speaker is Professor David Turner. I'm delighted to welcome him back to St Andrews. David Turner was one of the first members of this department way back in the dim and distant past, before most of us can remember. There is at least one person in the audience, two people in the audience, I think, who can remember that. So there is some memory, some institutional memory here. David Turner is one of the pioneers of functional programming. He did quite a lot of his research here. If you go to the library, the physics library, you'll still discover copies of books that apparently David Turner used when writing some of his early papers. So if you're very lucky and you're very interested, we'll go to the library at some point and point out the very books that David Turner used to write his papers. So we have some real functional programming history in this very area. David Turner needs almost no introduction to most of us. He's the pioneer, as I said, of functional programming. He has invented not one, not two, but three seminal functional programming languages. Sassel, that he did here, an untyped language. KRC, that he developed at the University of Kent. And, of course, Miranda, which is probably most well known. He's also written a number of excellent research papers. When I was a young PhD student, and I know it's hard to imagine that, but when I was a young PhD student, I would eagerly look forward to each of David's papers during the course of my career. They weren't very frequent, but every one was an absolute gem. David is a wonderful writer. The material he presents is absolutely engaging. All of his papers are worth reading, and that's a great tribute, I think. Very few of us could hope to have that said about us. So, David, I'm delighted to welcome you to St Andrews. David's going to talk to us for about 45 minutes on some history of functional programming languages. David.
Okay, it's a microphone.
It's a microphone.
Okay.
So now David is fully mic'd up. I've got the presentation.
Okay. Can you put down the big screen? Oh, yeah.
So it appears on the big screen.
Okay. Right. Let me just see if the size fits. Which way to go forward?
Right.
Something's happening. Oh, I see. Okay, I can do it on there.
Sorry.
I just want to make sure that you can see all the writing. No, it's gone off the bottom. You need to shrink it slightly. I use very big font and fill the slides, and other people don't. So make it just slightly smaller. No, that's wrong. Okay. Oh yeah, that was good. I'm going to change my glasses so I can see what's in front of me. Means I won't be able to see the back of the room, but I assume I'm still there. Okay, well, thank you very much to Kevin and the other organisers of the conference for inviting me. It's a pleasure to come back to St Andrews, where I started my career as an academic. I was here for 4 years, 72 to the end of 76, and I thoroughly enjoyed teaching at St Andrews and did some of my first research in functional programming here. Right, I was asked to talk about the history of functional programming languages, and so this is going to be perhaps slightly idiosyncratic history. There are lots of languages I won't mention because there have been so many functional languages altogether. So this is what I propose to cover. The lambda calculus is the beginning of the whole thing, of course, which was actually first appeared in a paper by Church in 1932, but I think the first full statement of the rules of the lambda calculus was in 1936, and his most often referred to paper, which is called the Calculi Lambda Conversion, was in 1941. How many people here have read Church 1941? Okay, that's my friend, yeah, good. And then I'll talk about this, and then I'll talk about ISWIM, which was Peter Landin's concept, which was a seminal concept in the development of functional programming and programming generally. A lot of things, including algebraic data types, started with ISWIM. And then I'll talk about POWER, which was effectively an implementation of ISWIM at MIT. Then I'll talk about SASL, which I did here. And meanwhile, some exciting things were happening at Edinburgh. And Miranda really brought those two streams together. And then from Miranda, we get to Haskell. Would I be right in assuming everyone here has seen Haskell? Or hands up everyone who knows Haskell. Yeah, almost everybody. Good. So I've only got one slide on Haskell because I assume you all know about it. Right, let's start with lambda calculus, which was devised before computers existed. It was an alternative foundation for mathematics based on functions rather than sets, which Church and Curry both worked on different versions of. The foundational language turned out to be inconsistent. It suffered from something analogous to the Russell paradox. But what survived was the calculus for talking about functions, which was just a part, originally it was embedded in the language that had propositions as well. And the lambda calculus has just variables, application, and abstraction, and there are these three rules. Our alpha conversion says that the bound variable doesn't matter. Lambda x dot e can be changed to lambda. You can change the x to a y systematically through the whole thing. The substitution operation, which I've denoted with square brackets, that substitute y for x in e, it's actually quite subtle. There are several pitfalls, but assuming you define that right, and that's the alpha conversion rule. You've got beta reduction, which says how you apply a function to an actual argument, and you've got eta reduction, which people often forget, but that's also important. Lambda x dot ex, where e does not contain x, can be simplified to e. That's interesting because you're reducing something under the lambda sign. All my languages have always done eta reduction. Haskell doesn't do eta reduction, for reasons that I might get onto or not. And it should, by the way. There are functional representations of natural numbers. You can write down lambda. I mean, you can add numbers and truth values and so on to the lambda calculus, but you don't need to. There are functional representations of all data types, including natural numbers. I assume most people will have seen that. Doesn't matter if you haven't. Three important results about the lambda calculus. The Church-Rosser theorem, which says, have I got any way of pointing? Anyway?
Yes, the black device, press the green button on top.
What green button? That? Oh yeah, oh good. That's much better. Yeah, so if A reduces to B and A also reduces to B dash, then there is a common destination C that B and B dash will both reduce to. And that implies, among other things, that if A has a normal form, it must be unique, because otherwise you wouldn't get this convergence property. So uniques of normal forms up to alpha conversion is a consequence of the Church-Rosser theorem, but Church-Rosser says more than that. Then the second Church-Rosser theorem says that if there is a normal form, you can always find it by repeatedly reducing the leftmost redox, which is called normal order reduction. That's important because that's telling you that you've got to do lazy evaluation in general if you want to find the normal form. Call by value, whether you reduce the actual parameter before you substitute it into the function body, is an incorrect reduction strategy for lambda calculus. People used it because it was more efficient, but you don't always get the answer. Bohm's theorem is very important. It's a separation theorem. It says if A and B have distinct beta-eta normal forms, there is a context which separates them. K is a function that if you apply it to x and y, it gives you x, and Ki applied to x and y gives you y. So this is telling you that there is a context which strongly separates A and B. You can put them in an if and get the then and the else branch. So that's telling us that alpha beta eta conversion is the strongest possible equational theory on normalizing terms. If you added to the lambda, so the lambda calculus is a theory of pure functions with a conversion, set of conversion rules that are the strongest possible conversion rules, in the sense that if you added a single extra equation between things that have different normal forms, the whole theory becomes inconsistent. So it's a very canonical theory. Right. Second Church-Foster theorem says that in general we must substitute actual parameters into function bodies unevaluated. Call by value is more efficient because the actual parameter is evaluated only once. Like that. Yeah, so if you have several copies of x, so you've got lambda x dot and then several copies of x inside, and you substitute in an actual parameter a, you'll then have several copies of a. And so seemingly the reduction happens several times over. And so people hit upon the plan of reducing the actual parameter to its normal form before you substitute it in, which is called by value. That's more efficient, but you don't always find the answer. The thesis of Wadsworth in 1971, and I was actually in the same building at the time, I was in the next year of Christopher Straiter's PhD students, Wadsworth showed that you could efficiently implement normal order reduction by doing it on graphs rather than on trees. Does that make sense to people? I'm sorry, I feel slightly frustrated not having a whiteboard.
There's a whiteboard there and
right, but then I'm not going to be able to change slides, am I? Because this isn't the way.
If you tell me when you want to change slides.
Oh, okay, thanks. Right. Do I have to carry this through?
Yeah, put it in the top.
Yeah, good idea. Okay, it's all this technology, it's very confusing. Okay, yeah, so lambda x dot, and you've got, let's say, 2 copies of x, and you apply it to A. If you do it naively, you end up with 2 copies of A, both of which have to be reduced. But what Wadsworth said was do it as a graph, so you end up with 2 pointers to A. Yeah? And so you only have to reduce it once. And Wadsworth did this in his thesis for lambda calculus. It's just one chapter of the thesis. Yeah, I'll come back there. I did it for combinators, which gives you a much simpler reduction machine. Substitution in the lambda calculus is a lot more complex than substitution for combinators. And then further development of that, Thomas Johnson in the 1980s showed how to extract program-specific combinators from the source text of the program, and then you compile your combinators into graph reduction that's running on stock hardware, which is a lot more efficient. And this was further developed by Simon Peyton Jones into the spineless tagless G machine, which underlies GHC, the Glasgow Haskell compiler. All the references are at the end, and I'll give these slides to Kevin so he can put them on the conference website. So you'll have the references. Right. In 1960, Lisp appeared. There's a paper by McCarthy in CACM called, what was it called? Recursive functions of symbolic expressions and their computation by machine. Very important paper. What was one of the first languages to do computation over symbolic data rather than over numbers and arrays. What you had in Lisp were S expressions And an S expression consists of atoms and pairing. But with atoms, atom was just a word, and the dot operation, which was a pairing operation, you can build arbitrary lists, trees, and graphs. Now, S expressions are of variable size and can outlive the procedure that creates them. So Lisp was about the first language to require a heap and a garbage collector. Then there was an M language, which is a simple recursive language that manipulates S expressions. It has const, which creates pairs, car and PIDA. These came from the machine that the thing was running on. Car was contents address register, and PIDA was contents of decrement register, but it was just the head and the tail of the pair, the left and the right side of the pair. You had various tests, like testing if something was an atom, conditional expressions, and recursion. So it was a purely functional language, and it was computationally complete. And in the paper, McCarthy shows how an arbitrary flowchart can be coded as mutually recursive functions. And that's a very important result. It shows how you can translate a Fortran program, basically, into a purely recursive function. The M language was first order. A lot of people don't realize that about this, but if you read the original paper and you look at the syntax of the M language, there's nothing in the syntax that allows you to pass a function as a parameter or return it as a result. The word lambda appears in this, 1960, but it wasn't lambda calculus. McCarthy's model was Klee's first order recursion equations, and he explained that in a conference I met McCarthy in 1982. People asked him why the scope rules were wrong in this, and he said it wasn't. At that time, he hadn't read Church's papers on lambda calculus, and his model was first order recursion equations. However, you could pass the M language programs were coded as S expressions and then interpreted by eval, and you could pass the code for a function to parameter to. So you get metaprogramming, in which you play games, in which you interpret code. You move between programs and between program and data. I find it very frustrating not being next to something I can write on. I just don't know how to do this. I'll just carry on talking from here. Where's my pointer finger? Over there. Right. It's all this. Okay. So some myths about Lisp. First of all, it's not the case, as many people imagine, that Lisp was originally pure and then added imperatives. Lisp actually had assignments and go-tos before it had conditional expressions and recursion. And Lisp programmers made frequent use of assignment. And Lisp was not based on the lambda calculus, it was based on first-order recursion equations. It acquired sort of higher-order capabilities because you could pass the S expression for a function as a parameter, but that doesn't give you the right binding powers. That doesn't give you the right scope rules. If a function has a free variable, say y, so here we have f equals lambda x dot x plus y, the y should be bound to whatever is in scope here, but there might be another y in scope where the function is called lower down. But you should get static binding. It's where the function is defined that y is bound. And Lisp got that wrong. It had dynamic binding. And if you think about the types, y might be an integer here, and when you call it further down, there might be another y that's a Boolean. Of course, Lisp was typeless, so that didn't matter. But dynamic binding is just wrong. It's not what the lambda calculus does, and you can't use the substitution rules don't work out. Not until the mid-70s were there versions of Lisp that had the correct binding rules. Okay, and I discovered this when I started using Lisp when I came to St Andrews. None of my Lisp programs worked. That's because I'd been taught the lambda calculus, I saw the word lambda in Lisp and assumed it was the lambda of the lambda calculus, and it wasn't. Which is why I invented Sassel. Okay, there's a slide here about the invention of closures. What time do I finish, by the way?
Got about 30 minutes.
I've got 30 minutes, okay. Right, so it took a while for people to figure out how to do static binding. Algol 60, which appeared in the same year as Lisp, actually, although it was an imperative language, it got the scope rules right. Algol 60 allowed textually nested procedures and passing as procedures as parameters, but not returning procedures as results. The Algol 60 report defines the semantics of procedures in terms of a copying rule, and this implies static binding. And the first people to figure out how to implement this were Randall and Russell. There's a book called The Implementation of Algol 60, published in 1964, it was a famous book, which showed how on the stack you have two chains. You have the dynamic chain, which links each function to the function that invoked it, and you have the static chain, which links each function to the function that is textually inside, which may be much further away on the stack. Okay, so F might have G inside it. F might call a lot of things which eventually call G. G has to be on the static chain. G has to be linked to this outer call of F. And there might be 16 function calls in between on the dynamic chain. So the static chain was an important discovery. And then the next step was Landin realized that if you have functions that return functions as results, you can't keep the static chain on the stack. You have to put it in the heap. And that was the invention of environments and closures. To pass a function around, what you have to pass around is a pair consisting of the code for the function and the environment in which the function was created. And that is what we now call a closure. And Landin invented closures in 1964. Landin wrote a seminal series of papers in the early 60s on the relationship between programming languages and lambda calculus. One of the papers was the translation of Algol 60 to lambda calculus, and another paper, that was the one he did in 64, showed how to implement the lambda calculus on a von Neumann machine, and that invented the SECD machine with the environment in the heap. SECD stands for Stack Environment Control Done. In 1966, Landin published the next 700 programming languages, which outlined a programming language schema. It was actually a programming language family, because you could choose constants and basic operations for your application area. So your constants might be numbers, or they might be words and lists and things. So it was a language family rather than a language. The important ideas in Iceland were, first of all, what Landin called church without lambda. He showed how to do lambda calculus without actually using the word lambda. So you could write let f of x equal stuff instead of writing f equals lambda x dot stuff. So his language had let, it had rep for functions that would call themselves, and if you wanted to declare several functions together, you could say let f equals stuff and let g y equals stuff. And you could also do it with where if you wanted to write out the expression and then define the functions afterwards. So with let, rep, and where, you could say anything you could say in the lambda calculus without actually using the word lambda. So I've shown an example there. And he invented the offside rule, so that you could have nested block structure without having to have all the begin ends that you had in Algol, or the squiggly brackets that were later used in C. And all my languages use the offside rule, and it also got into Haskell. So that's something now people now take for granted, is that you can show the structure of the program by nesting, by indenting, and it was Landin who invented that. Right. The ISWIM was described in 3 layers. The first layer was a purely functional language, a recursive language, church without lambda, as he called it, had conditional expressions, functions, and recursion. And then the next layer, you added mutable variables and assignments. And in the third layer, Landin added the J operator, which was something he invented. And the J operator allowed a function to capture its own continuation. It was later rediscovered in Lisp as call CC. But Landin had this idea in 1966. And he showed that you could write programs that, for example, jumped back into an earlier state of the same program. You could do backtracking. You could go back to a recursive procedure that you'd left, go back into the middle of it. And do astonishing things with these first-pass labels. Right, so ISWIM was sugared lambda calculus plus assignments plus a very powerful notion of control. At the end of the ISWIM paper, which is very well worth reading, 2 papers from the 60s that everyone who's interested in functional programming should read are McCarthy's Lisp paper and the ISWIM paper from 1966. And the references are at the end of my slides. At the end of McCarthy's paper, there is a discussion printed of a number of people, including Christopher Strachey, who was actually Landin's employer at the time. Strachey set up one of the first software consultancies, and he hired Landin as his programmer, and Landin wrote all these strange and wonderful programs doing things with lambda calculus. I don't think he did any of the jobs that Christopher had contracts for, but Christopher must have been a great boss because he let Landin do all this work on the lambda calculus while he was paying his wages. Anyway, there's a discussion at the end of the paper, and Strachey raises the idea of what he called a DL, a descriptive or denotational language. He says, what would happen if we didn't add the extra layers? What happens if we try to program just in sugared lambda calculus? And Strachey foresaw in 1966 that you could do that. You could have a purely functional language. And he wondered how hard it would be to program in that. And we now all know and love programming in Haskell or whatever. But the first inkling that that might be possible is in this discussion. So Strachey asked 7 questions about denotational or descriptive languages in that discussion, and it's well worth looking at. ISWIM itself wasn't implemented, but it inspired 2 languages based on those ideas. PAL, which was implemented at MIT, and Goduncan, which was, I think, was at Argonne National Laboratory. It was wherever John Reynolds was at the time. I studied PAL. I became Christopher Strachey's PhD student in about 1969. And he came back from MIT with the PAL tape and gave me that and said, play with that. And that was my original PhD topic. And I had great fun with these crazy first-class labels, writing strange backtracking programs and so on. And then I became more interested in the lambda calculus part. Anyway, what did PAL look like? It was sugared lambda calculus with let and where and rec and so on, just as Landin had showed. I think it had the offside rule. I can't remember now, but I may have got the offside rule from Landin's original paper. It had shallow pattern matching. So if expression returned a 3 list, or a 3 tuple, as it was called in PAL, you could break it open and name the parts, as I have done there. Yeah? Okay? And an obvious generalization of that is to allow X, Y, and Z themselves to be patterns. And I made that generalization, but it occurred to other people as well. So pattern matching started with Landin in the ISWIM paper, and then there are 2 ways to generalize it. One method of generalization is to do deep pattern matching, where you can have any number of layers of structure here to destructure a complex structure. And then the other way of generalizing pattern matching is to have multi-equation pattern matching. I'll come in a minute to how that got invented. Anyway, so you had applicative PAL, which was just the lambda calculus and tuples, conditional expressions and so on. Imperative PAL added assignment and musical variables, and then the next step was to add first-class labels. PAL got rid of the J operator. It just had labels and go-to, but labels were first-class citizens. You could pass a label as a parameter, return it as a result. So you could set a label inside a function, pass it out, and then jump back into the function from outside. PAL was typeless, which is what people said in those days, meaning the type checking was done at runtime. Okay. Right. I left Oxford in 1972 for a lectureship at St Andrews, and in the first term, which was the autumn term in 1972, what's the autumn term called? Was it Candlemas? Something weird. Martinmas, yeah, okay, I remember it had a strange name. But no, I call it the autumn term. You don't have terms, I have semesters, that's right. Yeah. Okay, anyway, I gave a lecture, a course on programming language theory, and during the course I invented a simple descriptive language, which was basically the applicative subset of PAL. Tony Daly, whom he passed away recently, but I hope many of you will have known him. Yeah. He was very excited by my sketch of a descriptive language. I came into work the next day, and Tony came up to me and said, "I've implemented it." And I said, "Implemented what?" He said, "That language you described on the blackboard." He said, "I've implemented it in Lisp," and he had. He wrote, the language didn't even have a name yet. I had to name it that day because it implemented it, and I called it St Andrews Static Language. He wrote a translator from Sassel to Lisp in Lisp, which turned out to be very easy because Lisp had all the right things. It wasn't terribly satisfactory as a teaching tool because if you made an error, you got Lisp diagnostics. So in the Easter back, I rewrote it as an SEC. I rewrote it in BCPL. I wrote a translator from Sassel, as the language was then called, to SECD machine code and a simple SECD machine code interpreter, all in BCPL, which was an ancestor of C. I brought BCPL with me from Oxford, and it was Tony Daly who got it working. And then we got Sassel working. Right, how does Sassel compare with the applicative subset of PAL? Well, I made two changes. I allowed multi-level pattern matching, so you could name the parts of a complex structure in one go, and that was nice. I'll give an example of that in a minute. But I got rid of strings. PAL had strings as a basic data type, and I decided to have characters instead, and that unifies lists and strings, because a string is then just a list of characters. So it means all the list processing functions that you write can also be used on strings. And that idea is carried forward from Sassel to Miranda and Haskell and other languages. Sassel was initially called by value, just for efficiency reasons, and I'm pretty sure I explained to the students that it really should have been called by name, but that was too slow. It had let and rec. There was no explicit lambda, I did church without lambda, and it had curried functions with left associative application. So I got rid of the brackets. And that has survived right through into languages like Haskell today. The data types, there were 5 data types: integers, truth values, characters, lists, and functions. And all data had the same right. So you had first-class functions, you could return a list as a result, and so on. And we used it for teaching functional programming for years, actually, instead of Lisp. Why was it better than Lisp? Well, first of all, it was a pure sugaring of lambda calculus with no imperative features and no eval quote nonsense. Eval quote gets you into a whole other game of metaprogramming, playing games between program and data, which is fascinating but has nothing to do with functional programming. Higher order functional programming is a completely different discipline from metaprogramming. And if you're thinking about lambda calculus, you don't actually want eval and quote at the same time. Sassel had correct scope calls for free variables, static, not dynamic, and it had multi-level pattern matching, which makes for a huge increase in readability. So here's a simple Sassel program. You've got a pair of pairs and you want to swap them over. So that A, B, C, D, well, X is a pair of pairs. You name the parts and then put them back together with the pairs swapped over. This is the Lisp code for it. I got this out of the book. It's generally a kosher Lisp code. I had to type it in. I used an old copy of Sassel because I needed to type this language, and it works. It does do the right thing, but it's just amazing you have to write all that instead of that. So pattern matching was a huge, multi-level pattern matching was a huge step forward. Nowadays it's commonplace, but in 1973, Sassel was probably unique in being a pure sugar and lambda calculus with multi-level pattern matching. It did runtime typing. Now, why everyone did runtime typing in those days in languages for handling symbolic data? And that's because if you're handling graphs and trees and lists and things, you want to write programs that are structurally polymorphic. A function which reverses a list or reverses a tree doesn't need to know about the types of the elements. And before Milner invented the polymorphic type checking type inference algorithm, the only way people knew how to do this was to leave the type checking until runtime, which I did in Sassel. And here's a little Sassel program from one of the early Sassel manuals. We've got a carried function of some unknown number of Boolean arguments, and we want to test if it's a tautology. That is, if it always returns the value true. And we can do that without knowing how many arguments it has. First of all, we test if it's a truth value itself. If it's a carried function of no arguments, that means it's already true or false. So the answer is, this is a conditional. So if f is logical, the answer is just f. And if f isn't logical, it must be a function. So we apply it to true and to false. And if both of those things are tautologous, then the whole thing is a tautology. Okay? So this is a rather neat piece of recursion, where the order of the function changes at each level of recursion. And you can't write that in any type language that I know of. Which goes to show that there are still things you can do in languages with runtime typing that can't be captured by any static typing system. And so that's why runtime typing still has its followers. Lisp hasn't gone away. And Erlang, for example, is a dynamically typed language. Do people know about Erlang? It's used to write the software for telephone exchanges. LM Ericsson have massive programs written in Erlang which run telephone systems of whole nations, and it's written in a weakly typed functional language called Erlang. Erlang is based on lambda calculus, but it has dynamic typing. Right, Sassel evolved. I'm going to have to speed up now. How much time have I got left? 10. Yeah. Okay. It's going to be very quick about the later languages. In 1976, Sassel became lazy. I decided to go for call by name using graph reduction. I bit the bullet, and my first implementation was a lazy SECD machine, which we knew how to do that. There's a book by Birch, published in 1975, called Recursive Programming Techniques, and if that isn't in the references, I'll add it before I put them on the website, which showed how to do what he called a procrastinating machine, which was a lazy SECD machine. I did that first. It was very slow, and then when I got to Kent, I re-implemented it using translation of Sassel to combinators, SK combinators, as in Curry's book from 1958, and then we do graph reduction of combinators, and that's fast. In fact, Miranda worked like that, and the Miranda interpreter is still twice as fast as Hugs. So I'm surprised that more people haven't picked up combinator reduction. It's very simple to implement, and of course it's nowhere near as fast as something like GHC, but if you want an interpreter, a fast interpreter combinator reduction is a good way to go. Okay, but I also added to Sassel at the same time multi-equation pattern matching, which gives you a lot more power, and I got that from John Darlington. Now, that's all the sites that ran Sassel. It spread from St Andrews to all these places. So it says in one of the early Haskell papers, I think Haskell report, that in 1987 there were no lazy languages running at more than one site. That's not true. Sassel got to about 30 sites. And Miranda was already at about 100 sites. Okay, So that's just to show you that Sassel escaped from St Andrews. Right. Meanwhile, in Edinburgh, also in the 1970s, Birstall invented a notation for algebraic data types. Algebraic data types were in the Iceland paper of 1966, but Landon had no syntax for it. Birstall gave it a syntax like this, which now looks very familiar. In fact, that's a generalized algebraic data type in Haskell, isn't it? Well, you'll find that syntax, first of all, in Birstall's 69 paper on structural induction. Birstall's PhD student, John Darlington, had the idea. Birstall used a case statement to test between, to do case analysis by different patterns, and Darlington changed it to multiple equations. So you could write this sort of thing in John Darlington's language, which was called NPL, New Programming Language, which was a first-order pure functional language for doing program transformation. It was strongly typed, monomorphically typed, but it also had set expressions. You could write this sort of thing, and that's where I got list comprehensions from. So John Darlington invented multiple equation pattern matching and what became list comprehensions. And this was all done in about 1975. And then, also at Edinburgh, Milner invented the polymorphic type discipline. It's Milner 78 is the paper. If I got that there, yeah. Lost it now, but it was on one of the slides. Milner 78, a discipline, it's called something like a polymorphic type discipline. People knew about polymorphic types years before. People wrote down type schemas for combinates, things like that. But nobody knew how to set boundaries to the polymorphism such that you would be able to do type inference. And it was Robin Milner who came up with this a simple system of polymorphism, which is what now called shallow polymorphism, but that turned out to be quite enough to do lots of interesting things, and it's decidable. And in fact, you don't even need to declare the types, you can do inference. And that was a massive step forward, which was first of all in ML, which was not a pure functional language, it was imperative, it had assignments. And then assignment, Hope was the next thing after NPL, Darlington's language. That group got together with David McQueen and others and made Hope, which was a higher order, purely functional language, strongly typed, and then standard ML put together the original ML and the ideas in Hope to make what is now standard ML, but that's not pure. It has functions and first part and exceptions, as you know. Meanwhile, I decided to put together Milner's typing algorithm with the work I'd done in Sassel, and that made Miranda, which was, I think, the first language that was both lazy and polymorphically typed. And Miranda is, if you can imagine Haskell with a slightly different syntax and without type classes, that is roughly what Miranda was. I changed from conditional expressions to conditional equations with guards. Okay, which is actually quite a bit more powerful, because if you've also got pattern matching going on, so X could have been a pattern, if you combine pattern matching and guards, you can express quite complex ideas in a simple way. And that, of course, carries over into Haskell. Guards first appeared in KLC, which was a miniaturized version of Sassel that I invented for teaching about 1980. KLC had only top-level function equations. There was no where. So it was effectively you had to do your own lambda lifting in KLC. So that sounds as though it would be very hard to program, but people managed to write quite complex programs in KLC. It was quite an amusing exercise, writing functional programs with only one level of function definition, no wheres. Anyway, when I put the wheres back in to make Miranda, that gave me, I had to puzzle for a bit. It cost me quite a bit of thinking. So how does the where go back into a structure like this? You don't want it to qualify an expression, you want it to qualify the whole guarded thing. So where attaches to this whole right-hand side. So whatever you define in the where clause, which goes down here, is in scope for all the equations and for all the different right-hand sides and their guards. and Haskell keeps that. But Haskell, let's see, let's jump over. Let's just, another change I introduced in Miranda, because of putting things together, you discover the needs for new things. I had to invent a lexical distinction between constructors and functions. So I make constructors begin with an uppercase letter. So that is a pattern match. X and Y are parts of stuff, but this is a function definition. No small letters is a function. X and Y, there are formal parameters. Okay, so Miranda was, or still is, lazy, purely functional, has list comprehensions, it's polymorphic with type inference and optional type specifications. Turner 86, overview of Miranda, gives a fairly full description of the language, and you can find that paper and free downloads of Miranda. It's at miranda.org.uk. Miranda.org was already taken by someone else in America for something that's got nothing to do with programming languages, but he kindly put a pointer to my miranda.org.uk on his website. Miranda was originally a commercial product, but it's now freely downloadable. Anyway, Haskell, which came on stream in the early 90s, and the first really practical implementations that people started using in a big way were about 94 and 95. I think Hugs was the 1st of April 95, is that right? No, it was Valentine's Day, that's right. It was the 17th of February. That's why it was called Hugs. It's a complicated joke. And GHC, the early versions of GHC were better about it. So how did Haskell work? It's similar in many ways to Miranda, but there are a number of important advances. First of all, the Haskell group decided to move the guards to the left-hand side of the equals. Now, that's in some ways more logical, because if you've got a pattern here, remember X could have been a pattern, you've got all the analysis together, the patterns and any tests that go with the patterns. That makes the scope rules for where slightly different. Where now has to cover not only the right-hand side, but also part of the left-hand side, because these things could be qualified by where down here. It extended Miranda's var constructor distinction into the language for types. So I used star, 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 star as an alphabet of type variables, which I got from the original ML. The original ML wrote its type variables like that. And when I designed Miranda in about 1983 to 85, and standard ML hadn't yet appeared, and standard ML started using lowercase. And Haskell had the same idea. It used lowercase identifiers for type variables and uppercase identifiers for types like integer and bool and so on. And it's a very simple idea, but it's a very big improvement in readability. This is a rather simple type, but once you get into complicated types, this star star stuff gets quite cumbersome, and Haskell's idea is much better. Pretty much everything that was in Miranda is in Haskell, sometimes with a different syntax, often with the same syntax. But Haskell has more things: type classes, monadic I/O, and a proper module system with two-level naming. And Haskell also has a richer syntax. I like designing small languages. So Miranda, for example, had only where, no let, and it had only pattern matching by equations, no case. Haskell is a richer language. It has let and where. It has multi-equation, pattern matching, and case, and so on. There's usually at least two ways of doing everything in Haskell, which is more to some people's taste. I always like to make my languages small. Haskell is not a big language compared with PL1 or whatever the current version of Fortran is. Yeah, okay, so what did I want to say more? And there's all my references. Right, now, let me go back. I've still got a few minutes, haven't I?
Yes, I've got that.
Yeah, trying to think what I left out. Oh yes, important things to say about laziness. Why did I make Sassel lazy in 1976? 1976, by coincidence, 3 implementations of lazy languages appeared. Henderson brought out, what was Henderson's paper called? Can't remember what Henderson's paper was, but I'll put it in the references if it already isn't, if it isn't already there. Friedman and Wise brought out a paper called Kant Should Not Evaluate Its Arguments, which showed the advantages of lazy evaluation in their dialectic list. Henderson had a purer dialectic list based on the lambda calculus that he also made lazy. Actually, his paper was called A Lazy Interpreter, and I implemented and wrote the manual for the first implementation of lazy Sassel on this. None of us knew about the other people's works, and we all discovered at the end of 1976 that practical implementations of lazy evaluation had been invented in 3 places. MIT, Henderson I think was in Newcastle, and in St Andrews. What's better about it? It's better for equational reasoning. If you've got an equation like f of x equals stuff, and then you apply f to a non-terminating expression. So if you have, say, f of x equals 3, and you apply f to something that doesn't terminate, f of x should still be 3, otherwise the equation isn't true. So equational reasoning works properly in a lazy language, doesn't work properly in a strict language. It allows interactive I/O, which I did in lazy Sassel and in Miranda, by lazy lists. And then the Haskell committee got the idea of monads and monadic I/O, which is actually significantly more elegant for doing interactive things. Although you can do it all with lazy lists, which is what we did in Sassel and in Miranda. But the really interesting thing, which came to me in the mid-70s, I started playing with lazy Sassel, is that all these exotic control structures that I had played with in PAL at Oxford when I was Strachan's PhD student, you don't need them, because with a lazy language, you don't need the J operator, you don't need call CC. Laziness does it for you. So there's something called the equal fringe problem. You've got 2 trees of different shapes, and they've both got tips. So around the edge, they've got numbers, say. And you want to find out if they have the same fringe, so the same sequence of numbers. Well, if you recurse down one tree, it's the wrong control structure for the other tree, and vice versa. So using complicated control structures, people invented something called coroutines. So you'd have 2 recursive programs which talk to each other. Well, in a lazy language, you don't do that. You just create 2 lists, the fringes of the 2 trees, and then compare them. And because of laziness, it only explores each tree until the first mismatch, and then stops. And the list of successes method gets rid of backtracking. Instead of having a backtracking program, you write a program that computes all the answers at each level of recursion, but you only look for the first one. And because of laziness, you in effect get the backtracking for free. And the first program that uses the list of successes method is actually one of the examples in the 1976 Sassel manual. It's a second way of doing the 8 queens problem. But I didn't have a name for it. And Phil Wadler came up with the phrase, replacing a failure by a list of successes. And then it's interesting how if you name something, people are much more inclined to understand it and to use it. Okay, so I think lazy evaluation is the greatest thing since sliced bread. And I think perhaps my main contribution to functional programming was to put lazy evaluation on the map. Because what lazy Sassel showed, and all the sites that took it, and Burroughs Corporation had a major project, they built a machine to do combinatorial reduction, so they could run lazy Sassel programs. It showed that lazy evaluation was practical, and that made pure functional programming practical, because all the things that you can't do in a strict language and make you think that you have to add imperative features, if you go lazy, you can stay pure. And there's a very nice talk by Simon Peyton-Jones about the history of Haskell, which he gave about 1985. I can't remember was maybe at a Popple conference or something, in which he makes that point that purity and laziness go together. You actually can't add side effects to a lazy program because you have no control over the order of evaluation, so you don't know when the side effects are going to happen. So the two virtues feed off each other. Okay, I better stop now to allow some time for questions.
Thank you, David. So we have time for a few questions from the audience.
And there's 3 pages of references at the end. And I'll add some more if there are any I forgot.
Simon.
David,
Yeah, look at my glasses, other glasses. Yes.
if you were giving this talk in 20 years...
Oh, hello, Simon.
Hi, yes.
Hi.
If you were giving this talk in 20 years' time,
Yes.
what do you think you'd be talking about?
Oh, right. Why type glasses were a really bad idea and the neck language got rid of them. Type glasses are the most interesting thing in Haskell, but I actually think they were a mistake. But that's another talk.
I'd like to hear that. Are there other questions? John.
So David, you haven't said anything about total function.
Oh, hello, John. Gosh, there are all these people that I know. You see, I had my reading glasses on when I gave the talk, so it was all a blur. Yeah, I haven't said anything about total function.
No.
No.
What would you say? You had another few minutes to talk about that.
Oh, well, that's another talk, but yes. An interesting question is, can you get rid of bottom? Because what we're doing with lazy evaluation is we're exploring what people call co-data. For example, there are lists, which are finite, and there are co-lists, which are lists that go on forever. But what you have in Miranda or Haskell are lists that might go on forever or might end with a bottom. So we're using what you might call weak data types where bottom can pop up at any point, actually to do programming with co-data. And co-data is, you can write programs with co-data that never produce bottoms. There's a sort of dual discipline. You've got structural recursion, which is recursion that always terminates, and there's a notion of structural co-recursion. I wrote a paper giving quite a simple explanation of all this. And what is that paper called? Do you remember, John? It was originally in 1995, and then it became a journal paper in 2004. And it's in the Journal of Universal Computer Science. Well, let's take another question if I remember what the paper is called. But anyway, I think, yes, another thing that I might say, I won't be giving this talk in 20 years' time because I'll be too old. But another thing that people might be saying in 20 years' time was how we got rid of bottom because we added co-data, we added data and co-data as two separate types, two separate systems of types, and got rid of bottom. So effectively that enables you to keep the lazy and the strict parts of the program separate in a clean way through the type system.
Was the paper called Total Functional Programming?
Yes, it's just called Total Functional Programming, that's right.
Simple.
Yeah.
Okay. Is there a very quick question? No, then I think we should thank David very much. David will be here for the whole of TFP. There'll be a chance to chat to him. We've scheduled a very short break now. I think we keep it to just a couple of minutes.